Okay, so welcome, folks. So again, this week kicks off the discussion of advanced topics, so to speak. You're really done seeing most or really all of the fundamentals of quantum computing. So now this week and in the following few weeks, we'll be exploring more general topics within quantum computing and beyond that are a little more advanced. Quantum error correction is arguably one of the most important topics in helping us get to full fault-tolerant quantum computers. So it really felt like a good one to start off with. Before diving into today, I would love to just get a feeling from everybody what you thought of lecture and what you've felt about this topic so far. In particular, I would love for everyone to just send a number in the chat, 1 through 5. What are you feeling about it? 1 being, I really find this very boring, or I don't like it. 5 being, it's amazing, I love this topic, one of my favorites. And of course, anything in between is fair. So go ahead and send that to the group if you're comfortable, or me if you would rather. But I'd love to go ahead and just get that feedback, just kind of hear what people are feeling about this. And again, it's totally fine if this topic is just not for you so far, or if it's like your favorite topic of all time, then we'd definitely love to hear that as well. Getting a solid stream of 4s here. Ooh, a nice little 3.9. Appreciate the precision. Okay. Okay, so people seem to be enjoying it overall. I'll say that starting this week, really more so than any of the other weeks, this is really for you all to just start exploring some very advanced topics. I mean, everything we've learned has been advanced, but a lot of it has been very crucial for you in building up a foundation. And at this point, you've seen all of the foundation, really. So now we're exploring these more advanced topics. And all of that is to say that if there's something you're really curious about here, if I make a specific point, I am more than happy to really dive into that, to talk through it. So long as we're all interested in talking about it, I am more than glad to do that. So let's go ahead and get started, but please do, if you have any comments or questions, go ahead and write them in the chat or unmute and ask. So again, today we're going to look at actually another quantum bit flip code. We'll discuss why we're saying another in a moment, if it's not clear yet. And then we'll look at Qiskit noise models, specifically how to implement noise models in Qiskit. Before diving into the technical content, there's just a few announcements. I believe this link actually was not ready as of last week, so I will make sure it goes to you now. I'll send it in the chat as well. I'm just putting it in there, making sure it's right. Yeah, that looks good. There you go. So yeah, we have a Quantum Ambassadors program, which is a very exciting way for you all to continue in your kind of quantum journey and your relationship with us. So please do go ahead and consider applying to this program using that link there. Furthermore, this Sunday, we will have a TA undergraduate and graduate panel. So you can hear from many of our wonderful other TAs, meet some of them and hear what their journey has been. So that is an awesome opportunity right at 2 p.m. So a little after lecture is done. So again, as usual for us, 2 p.m. Eastern time, that is. And if you didn't already get it, here's the attendance code. I will also type this in the chat. So you have it, 1944. 1944 is the attendance code. Okay. So without further ado, let's dive in. Let's get started. So we're going to start by looking at another bit flip code. And again, what I mean by another will become clear in a moment. So Let's start by reviewing the repetition code circuit that you saw in lecture. So this is the repetition code circuit, where you have your code qubits, Q0 and Q1. We're calling them code qubits because they encode the information, the logical qubit information, right? There are repetitions. So we apply the same things to them each. And then we have this auxiliary, which is kind of a fancy word for extra qubit, where we tie them together using C naughts. We relate them using C naughts. And then at the end, we measure. And we store the result of that in a classical bit called the syndrome bit. So again, we're getting into more advanced topics here, and there's a lot of vocabulary and extra terminology. It's really important here not to get bogged down in every single term, but rather just to try to keep absorbing more as you go. Of course, I'm always glad to dive more deeply into these details, but I just want to highlight that if you're feeling a little overwhelmed by just on this page alone, the number of new terms and everything, that's okay. We can keep talking about it. You can keep exploring it. We really want to make sure you at least hear these terms, see them in context. You can start getting a feel for these more advanced topics. But really, to me, importantly in this circuit, we have some part of it where we run our quantum circuit and potentially we get some errors, right? In an ideal world, there'd be no errors, but that's really not realistic. We are going to probably get some errors, particularly in the short term, but even in the long term. And then what we do is we apply C naught gates between the code bits and the auxiliary qubits. And effectively, very loosely, very generally, I think of these as each tying them together, relating them. Really, generally, we can call this a form of entanglement. Whether it's a kind of quantum entanglement or not might depend specifically on the previous gates and things like that. But generally, it is entangling them. It is correlating them. These are relating these qubits in a very particular way, which, as we saw in lecture, means that when you measure the auxiliary qubit, you can actually measure whether there was an error or not. In particular, we can basically go through this table and see that when both of the code bits are 0, we go back here, code qubit is 0, and the auxiliary qubit starts as 0, right? It always starts as 0. Then this C naught does absolutely nothing, right? The control is 0, the target is 0, the C naught does nothing. Then if the other code bit is also 0, the next C naught also does nothing. So if by this point in the circuit, when you're just about to run the C naught gates, if all of your qubits are 0, you might as well not have these C naught gates there in terms of what happens, right? They don't do anything. So then you measure and you should get out 0. However, if one of them is 1, right? If this one's 0, okay, then we get 0 out. But if this code qubit Q1 is in the 1 state, that means the control qubit is now in the 1 state, which means we do apply an X, right? The rule of C naught is that the control is turned on when the qubit is 1, and that effectively turns on the X gate to the auxiliary here. So then we flip it, and we in fact get a 1 out. Now, it really doesn't actually matter which code qubit is 0 or 1. All that matters is if one of them is 1 and the other is 0, you will get a 1 out. However, if they're both 1, then actually they cancel each other out. We flip it, and then we flip it back, in other words. And by it, I mean the auxiliary qubit in particular. So if both of them are 1, if both of the code qubits are 1, then we flip with the first C naught, and then we flip back, and we end up getting 0 out for our syndrome bit, right? In other words, our syndrome bit is 0 when the code qubits agree, and it's 1 when they disagree. So we can think of this syndrome bit as basically telling us, Do they agree or not? Do they match or not? So in other words, the state of the syndrome bit, which we also call the error syndrome, tells us if the code qubits are the same or if a qubit flip error occurred, right? The only way we could possibly get this in a repetition code where these qubits are meant to be the same is that one of them flipped. One of them has incurred a qubit flip error. And so basically the syndrome bit kind of sets off these alarms of, hey, I found something, I found an error, right? In this case, particularly a qubit flip error. So again, this is still review from the lecture, but it's just important to see these things several times, as well as to hear some of this language, particularly around syndrome and things like this. One thing I want to clarify, because we're going to be using some new terminology today that is very common in the error correction community, is about bit flips. So in full, we could actually call that code we just looked at a bit flip repetition code. I know that's quite a mouthful. There's a lot of terms there, but that's most generally what that is. Because this code only corrects for bit flips, it doesn't take care of any other kind of errors, we call it a bit flip code, right? Specifically, it's an error correcting code that corrects for bit flips, so we call it a bit flip code. But we could also have sign flips. For instance, the plus state going to the minus state or vice versa. You will in fact see these in the homework this week. These are generally called phase flips because that minus or plus sign is a phase between states. You could also have an arbitrary or really just general error code that corrects for any errors. And of course, this is really the goal. We want an error correcting code that corrects for all possible errors, doesn't matter what kind it is. Most of those build off correcting for a specific type of error. So oftentimes you can understand how the general one will work by understanding how it works for, say, a bit flip or a phase flip. So we often start by looking at bit flip codes because they're just the most intuitive. They really are something we see in classical error correction as well. And seeing how you move from them, how you move from classical to quantum is a good first step. And then you can see how to generalize. So it's a bit flip code because it corrects only for bit flips. But it's also a repetition code because the way that it does it, the specific technique, is using repetition, right? So we call it a bit flip repetition code. Note that you could also have a phase flip repetition code, which again is the content of the homework this week. So it corrects for phase flips, but it's still a repetition code. Note you could also have a bit flip code that is of a completely different technique that uses something like more advanced terms like the stabilizer formalism or something like this that we won't go into here. So I just want to clarify some of this terminology for you all. Any questions so far, whether it's about the content that we reviewed from lecture or about this terminology so far? Any questions? Okay. All right, seems like we're doing well then. So one thing I really want to point out here, and that's going to be our discussion today in large part, is there's actually a variety of bit flip repetition codes. So this one that we've seen is actually not the only bit flip repetition code. As specific as it sounds, bit flip repetition code, it's actually one of many. There are many different bit flip repetition codes, each of which has their own pros and cons. So one thing that we're going to do today is we're going to look at a different bit flip repetition code that tackles one of the weaknesses of this particular approach. So basically, by the end of this week, you'll have seen two different approaches to this for quantum error correcting codes, both of which offer some hopefully very valuable insights into how error correction works. So I'm curious to hear from you all. What do you think might be some weaknesses of the code here? And again, this is the exact same one that we saw in lecture. So basically the one we saw in lecture, what are some weaknesses of it? for a bit flip repetition code? And there are multiple answers here. There's not one correct answer necessarily. So I'm just curious to hear from folks. Again, feel free to send it in the group or to me individually if you feel more comfortable. But basically, I'd just love to take a moment to hear from folks. What do you think might be a weakness of this code? What's something we could maybe improve? And if you're not sure, that's also totally fine to say. Yeah, so this is a good point. Thank you, Wayne. Yeah, if both of the qubits are flipped, then the error is not detected, right? Really, right now, this is able to detect if the code qubits disagree with each other, if they don't match. But if both of them got flipped, they'll still match each other. For instance, if we want these to be in the zero state, 0, 0, but they both flip, they'll both go to 1, and we will not detect that. This is a very good point. This is definitely a weakness of this code. It actually does not protect against all types of bit flips. It really only protects against single bit flips, as in only one of them are allowed to flip. So even more specifically, this is a single bit flip repetition code. Of course, you can keep getting more and more descriptive here. But it's a very good point. I will say that generally we would have to look at our specific case to know if that's acceptable or not. Because for instance, if we have a given likelihood, like 50% chance that one of these qubits flips, the chances that both of them flip are even smaller. In that case, it would be 25% or a quarter, right? So just by having more repetitions, we decrease the chances of running into this issue where too many bits flipped, where there were too many errors. So this is actually another aspect that we won't dive into today, related to something that's known as distance of a code. But basically, in error correcting codes, you can also kind of talk about the quality of it or the weakness of it by exactly this. How many errors can it handle before it breaks? And as we saw in lecture, generally repetition codes like this, both classical and quantum, it's not really a quantum thing specifically, but just any type of repetition code generally can handle up to half of the bits flipping, up to half of the repetitions flipping. Once you get half or more, then usually the code fails and it tells you the wrong thing, right? So there are other techniques you can use for that. Today, we're not going to focus on it, and we'll go ahead and say, let's assume that the odds of one of them flipping is high enough that we're worried about it, but not so high that we think both would flip at the same time. However, it certainly is a concern in general quantum computing. I'm going to point out a different piece that maybe you hadn't thought about, or maybe you had, which is the measurement component. So I'm actually okay with all of this. I'm going to say for now, I'm okay in assuming that at most one bit flip occurs, but the measurement is actually something that's bothering me. So again, there are many answers to this question. The ones you brought up and many others are completely valid here, right? But today, I really want to point out something very different, which is focusing on avoiding this syndrome measurement altogether. So I want to take 1 second to just talk about why this is a weakness at all. To do this, we have to review the noise that comes with measurement. In particular, to measure qubits, we have to temporarily open them up to the environment so that we can measure their state, right? If you remember from our hardware lecture, we keep qubits in very cold or otherwise very isolated, protected places. Quantum information is very fragile and we need to protect it as much as possible. But to measure, you're kind of forcing your hand here. You have to open them up. You have to look at them. That's the whole point of measurement. So in doing this, you actually leave them more vulnerable to errors. Just the act of measuring them alone basically opens them up and makes them way more vulnerable. We call these measurement or readout errors, if you happen to remember. But the more important thing is that really measurement in general can bring about errors. These are actually some of the biggest errors that we face in our current technology. We're getting better and better at really protecting the qubits when they're computing and processing, but when we actually want to measure them, it's really hard. It just is very difficult. So let's see if we can just avoid this altogether. Just a bit flip repetition code that actually avoids measurement at all. To do this, I want to break down the 5-step process that we at least quickly defined in lecture for quantum error correction. And the point here, why I'm bringing this back up, is not that it's strictly necessary for this code, but generally, as you go on and may be curious to learn about more and different error correcting codes, it can be very complicated. There can be a lot of different techniques out there and mathematical pieces and theories. And so it's helpful to just have one framework to look at any error correcting code. First, any error correction scheme deals with encoding. You have to first decide, how am I going to encode my logical states and the gates into physical ones, physical states and gates. Then, once you've done this encoding, you go ahead and you send your qubits out. You say, you know what, good luck. I'm going to do my computation. I'm going to send them over there. Whatever the case is, basically, the physical state is exposed to noise and it may incur errors. Of course, we hope it doesn't, but the whole point of this is that realistically, it probably will in some cases, enough that we need to do something about it. So then we want to detect the errors. So any errors in the state are detected and diagnosed in some sense, sometimes more specifically and other times not, but we generally use the error syndrome for this. Then after we've detected the errors, that's great and all, but we actually want to correct for them as well. We not only want to say, yes, I found an error, but also, can I fix it? So we fix those errors. And lastly, we decode the final state in its logical form, right? So this is really undoing that initial step of encoding. So encoding starts the whole process. Then we potentially get ourselves some noise and errors. We detect any errors, correct them, and we end the whole process by decoding, which again is undoing that first step. So here is going to be our new bit flip repetition code for today. This is the primary content for today. The point is not for you to memorize this circuit in particular, but rather just to show you how we can start analyzing new codes that we might not be otherwise familiar with using this way of breaking things down. So first of all, I'll walk through which pieces correspond to which step. We're going to call these first two C0 gates the encoding step. We're encoding Q0 into these qubits. Then we send our qubits over a noisy channel. This is kind of technical terminology, but generally this is just saying we run our quantum circuit and potentially incur some errors. Then we're going to detect any errors, actually just using two C0 gates. So notice that at least this part from quantum circuit to our detection steps look very similar to what we had before. And then we actually have a new gate here that we're going to briefly discuss today. I'll get into that for a moment, but generally what I would like you to focus on now is just that this last bit does the correction for us, very importantly, with no measurement. So at no point do we measure, right? In our previous version, we basically encoded somehow and then had our sending over a noisy channel, our detection, but part of our detection involved measurement, right? And then from there, we kind of did some classical things for correction and decoding. But at the end of the day, in this version, we're correcting for the same kinds of errors, but not using any measurement. And again, that could end up saving us from a lot of other errors that creep in, because measurement in of itself is a very noisy process. So I'm not expecting this circuit to make sense right now, but we're going to actually walk through implementing this ourselves in Qiskit. And then if you would like, we can walk through how this actually works theoretically as well. But before we do this, I do want to just point out and name that this is a new gate for us. This is actually a 3-qubit gate, the first that we're seeing, and really the last one that we'll see. There are not many of these that we usually talk about, but this is an important one, so it felt worth bringing up with you all. This is a 3-qubit controlled X gate. It's also called the Toffoli gate, named after a scientist, Toffoli, or I believe a mathematician. It's actually just the same as a CX gate, a controlled X gate that we've been learning about for months and months. But now we have 2 controlled qubits, and they must both be 1 to flip the target. So notice that our normal CNOT can connect any 2 qubits with our control and then our X gate that's targeted. Here, we just have 2 controls, and they both have to be on. So we're basically just giving control to multiple qubits here for the same exact action. We apply an X if both of these are 1, and otherwise we do nothing. So although it may seem a little complicated, we haven't seen 3-qubit gates yet, this is actually relatively straightforward. It's basically what you've already seen, but it is controlled by multiple qubits. And this will actually turn out to be very helpful for us here. This is also a very common gate when talking about quantum computing, at least in theory. Although, as we will see, or at least I'll mention later on, it's practically a little difficult to build. So we don't use it a lot in hardware, but at least in theory, we use it a lot because it's quite useful. So enough talking about all this, let's actually implement it. So go ahead and move to the IBM Quantum Experience, and let's get our notebooks open. I will also go ahead and send the notebook here in case you did not already get it. Oh, wait. That's the wrong one. Where's 21? Okay. There we are. Okay, there you go. And yes, the attendance code was 1944. Okay, so go ahead and open up this notebook in IBM Quantum Experience if you haven't already, and let's start going through this. So first of all, we have to do our imports as usual. I'm going to go ahead and run in the solutions version to make this a little faster. Make sure you get this libraries imported successfully piece. Okay. Now, in this part, we're going to go through this bit flip code that we just looked at briefly. And I know we looked at it briefly, but we're going to follow our 5 steps and see if we can understand this piece by piece. So the first piece is encoding, right? And maybe I will go over here, actually. Our first piece is encoding. So in this, we want to accomplish 2 things. First of all, we want to initialize a circuit with 3 qubits and 1 classical bit. So this is something we've been doing all year. This would be quantum circuit, not circuit, circuit 3,1, right? 3 qubits, 1 classical bit. Here, we're actually adding a classical bit that we don't have to technically, but we're adding it so that in the end, we can simulate and measure the results. So technically, this classical bit isn't needed at all. The whole point is we don't want to measure anything, but at some point you may want to actually measure the result of your error corrected qubit. And so you have to do a measurement at some point. So this is the 1 classical bit, but that's just for us to check how this is working. It is not a necessary part of the error correction itself. The 3 qubits, on the other hand, are, because this is going to be a 3 qubit bit flip code, meaning it corrects for bit flips, technically single bit flips, using 3 qubits, so 3 repetitions. Then we want to entangle the state of Q0, Q0 with the other 2 qubits. So we can actually do this by simply doing CF skates. We can assume that generally our first qubit, our 0th qubit, will be in any old state, and we basically just entangle them in just a general sense, like this. We basically just relate the 0th qubit with both the first and the second qubits. And in this way, we effectively transfer the state over to them or spread it out amongst them, however you would like to look at this. But you can actually walk through the math and show that truly this is generically entangling qubit 0, 1, and 2. Again, we can walk through the theory of this in the slides after and actually show, or I would encourage you to do this on your own after lab, but to actually walk through this circuit and show that for a general state, this is truly entangling these 3 qubits so that we now have just the logical 0 state and the logical 1 state. So this is actually step 1. We create our circuit, we entangle qubits 0, 1, and 2, and here's what we've got. Again, the barrier, if you happen to remember from last week, is just a nice visual tool. There's nothing deep to it or anything, and we provided it for you because you're not responsible for knowing that. But it just helps to visualize the different pieces, the logical steps. All right, I'll keep moving, but again, please do ask any questions as they come up. Now, for step 2, this is when we send over a noisy channel. So we want to simulate a bit flip error on Q0 in this particular case. So what I would love to hear from folks, and you did see something like this or exactly this in the lecture, but what does a qubit flip error look like? In particular, what gate flips a qubit from 0 to 1, for instance? It's meant to be in the 0 state, but it flips to 1. What gate does that? Go ahead and write in the chat or unmute. What gate do we know that does that? And I'll go ahead and zoom in as well, because I know sometimes this is hard to read. I don't know if that's too much, but. Yeah, thank you very much. Yeah, it's an X gate, right? So we'll use an X gate to sort of simulate this bit flip error, as in technically any X gate we'd want to apply, we'd have to apply to all our physical qubits. But here we're simulating some sort of noise creeping into our system and basically applying an X gate that we didn't want. Right? That's really one way to think of errors and noise. Noise generally is like gates being applied to our qubits that we didn't want applied. That's basically what they are, but they can come in many different forms and be much more complicated than the gates we've seen. However, a bit flip error is you're your simple X gate. It flips zeros to ones and vice versa. Okay. So basically we have our encoding here on the left, and then this part represents our error that we incur. Okay, now we go to step 3, error detection. We want to detect if an error actually occurred here. So we're going to do this by checking what's called the parity, which is really just a fancy word that we have mentioned before, but it's a fancy word for, do they agree with each other or are they different? Do the qubits match each other or not? If the qubits match each other, if they agree with each other, we say that they have a parity of 0. If they are different from each other, then we say they have a parity of 1. This is actually what the syndrome bit was telling us in the previous version of the bit flip code. So now we'll go ahead and say bit flip circuit. And we now need to check this. And as we've said here, actually, we've provided for you, we have to use C NOT gates. So we go ahead and do this. And we're basically in this line checking, do 0 and 1 agree with each other? Do the 0 qubit and 1 qubit agree with each other? That is a different way of thinking of the C NOT gate, but it's an equally valid way. Now, of course, that's a little more complicated when we're dealing with quantum states in some sense, because you could have a superposition of answers to that question. But basically, this checks if they agree with each other. And then we can do the same thing here. So now we've gotten this circuit out. And again, this piece so far is actually more or less identical to the code we had, but we stop there with our detection. We don't measure anything here, right? Before we measured after applying 2 C NOTs just like this, or at least similar to this, but now we're going to do something a little different. We're going to correct within the circuit without ever measuring, without ever looking at what the relationships are. So in this step, we're now going from detecting to correcting. And this is where we're going to use our new gate, the controlled X, QxQ, or Toffoli. This gate has a bunch of different names, but for Qiskit, it's QxQ, which I rather like because it follows with CX, where we have our control X, this is our controlled. So what we do is we specify our first 2 control bits. Those are 2 and 1, and we're targeting 0. So this is a 3 qubit gate, meaning we have to apply this to 3 qubits. We have to tell Qiskit which 3 qubits are we applying this to. So again, this is the first time we're seeing a 3 qubit gate. So it's okay if this is a little more confusing.
Can you go up real quick?
Yeah, so this is basically, going back to the slides here, this is going to be the same as this gate. Or did you ask to move up?
I'll move up.
Move up, yeah.
Okay, thank you.
Yep, no problem. So yeah, so this will be our gate through error direction, yeah.
All right, thank you.
Then we apply our QxQ or Toffoli as it's often called. And so our circuit should look like this. Again, this should be looking very similar to the version that we saw in the slides, where now we're specifying that our quantum circuit is actually nothing. We're not trying to do anything, but we get an error that's our bit flip on the 0th qubit. And that's it. From here, we decode the final state. Now, very importantly, what this step is doing, because I know that this may be a little unclear so far, what this step is doing is it's detecting if any of these qubits disagree with each other. And if they do, what it's doing is then flipping the 0th qubit. So it's saying if the 0th qubit disagreed with either of these, then there must have been a bit flip. And so now we have to flip the result here. We're going to flip here. So in some sense, there's a slightly different dynamic going on between these qubits, as we saw in lecture, because in the end, the logical state is actually just stored in the 0th qubit. That's what this ultimately does. It's basically saying, if I found disagreement amongst any of these qubits, I'm going to go ahead and flip the 0th qubit because I'm going to say that that has to be fixed. So, okay. So the 0th qubit stores the logical state. That actually means decoding is a lot easier here than before because we don't have to take votes or anything like that. In some sense, the Toffoli gate is kind of like a majority vote here. It's like a majority vote on whether they agree or disagree with each other. And so we can actually decode by just measuring Q0. Again, the measurement is not part of the scheme so much as it is if we want to know what the final logical state is after decoding, then we have to get this measurement result out. But we could also just go ahead and use this within some circuit. And basically, every single time we want to apply a gate or a set of gates, we could just sandwich them here in step 2, and then run this on either end, the encoding, the error detection, correction, and then when we're finally done, we can decode like this. Let's go ahead and do this. And notice we get 0 out. What we're doing here is we're measuring, notice, just the 0th qubit. We don't care about the other twos. They're kind of more internal in this. We're just measuring the 0 qubit, and yet it's always in the 0 state, even though we applied an X to it. That's because this error was detected and then corrected. And even if you're not entirely sure how every single one of these gates comes together to accomplish that at the moment, you can see just factually, at least according to our simulation, that it does seem to work. Because if we didn't have all of this in here and we just applied our X gate to Q0, we should actually get 1 100% of the time, because we have 100% of the time we've made this circuit, put in X gate in, put in a bit flip error. So in fact, we can see here that through effectively the magic, seemingly, of this circuit, we have been able to correct that error 100% of the time and always get a 0 out. Now, what I'd like to do is basically take a look at the code, which first of all, we've provided in full here. This is all the code that we just built step by step by step, put into one cell here so you can really see it all in a row. Again, steps 1, 2, 3, 4, and 5. But now I want us to modify this so that we're actually using the logical qubit in the 1 state. Does anyone have any idea, first of all, of what part of the code we're going to change? What generally do we have to do here to change what the logical qubit's state is? It was 0 before. That was the assumption, that was the starting point. But now I'm saying I want to change it to the logical qubit, not the physical ones. The logical one is definitely in the 1 state. What do I have to do to this code here that you also have in your notebook? What do we have to do? What do we think?
The execute before
Ooh, yeah. So, okay, I heard some X's in there. Yeah, certainly. So we have to really focus on the encoding step, first of all. By the time we get to the noisy channel, it's too late. We've moved past the logical qubit. All of these internal steps are really dealing with the physical qubits. The encoding and the decoding is where we go from logical to physical qubits. That's encoding, or decoding is going from the physical to the logical qubits. So if we want to change our logical state, that's something we do right away. Generally, the best way to do this, or a way to do this, a standard way, is encode, and then, not like that, and then basically apply that logical gate, whatever you need, to all of the physical qubits. So in this case, if we want to go from 0 to 1 on purpose, the logical gate, then we're going to apply an x. But very importantly, at this point, after these CXs, we've encoded. So going to the 1 state is really not a matter of individually addressing qubits so much as changing all of them. So we want to do something like this. We want to apply an x to all 3. Now, for what it's worth, as a side note, if we were building hardware, quantum hardware with error correction in mind like this, we would actually probably create some sort of one gate that we just knew as X. You and me from the software side knew as X, but under the surface was effectively doing this, applying an X to all 3 at once. Long term, that's the goal, that you and I don't need to encode quantum error correction into our circuits and do all of this complicated stuff, but that all of this is actually built into the hardware itself. But for now, it's good to have an understanding of that, and in all reality, we're probably a long ways off from that being standardized. So this is how we go from the logical state 0 to the logical state 1. Very importantly, notice that it is different than getting a bit flip error. This is a logical bit flip, an intentional bit flip. This is a bit flip error because it only hits one of them. We'd be very unlucky if it hit all 3 of them, but in this case, it's very unlikely. So now we can go ahead and, first of all, compile this circuit, where again, we encode them in the 1 state. So we encode them so they all agree with each other, and then we go into the 1 state. Then we can simulate this. And now we see 100% of the time we get the 1 state out, even though we did still get that bit flip error in there. So this bit flip error was totally fine. It did not cause a problem here. I'll note that as anything that starts to get this advanced, there's a lot of different ways to do this. So you could probably find other ways to encode the 1 state. For instance, you could do it on 1 qubit before encoding, but this is actually a more general approach to do it, where you act on the physical qubits altogether. Okay. Now, there are other optional exercises provided here, number 2, 3, 4, and then there's some follow-up activities for you to consider. I want to go ahead and take the last few minutes here to step back from this and kind of have a discussion more generally, but do know that these are here. They're there for you to practice. The solutions will ultimately contain answers to those parts, but I also encourage you to explore those on your own after lab. So now I'm going to move back here, and I just want to generalize the pros and cons of this code. So again, every single error correction code has its pros and cons. It's not like we just solved the measurement problem and now it's all perfect and wonderful. So here's some important ones to consider in this case, some pros and cons. First of all, we can detect and correct anything up to half of the qubits incurring a bit flip. And I really encourage you to take some time to walk through why that is. It's a little subtle, but I promise you that if you walk through it, you can see it. Furthermore, and this was the big one that we introduced today, it doesn't require measurement for detection or correction. We never opened up the qubits to this very vulnerable, noisy place after measurement until we were done with everything, right? At the end of the day, we're always going to need to measure our quantum computers because we want to know what they're doing. Otherwise, they would be useless, black boxes, right? But we've basically limited it to only the absolute necessary measurements. They're not part of the error correction scheme itself. Also notice that this doesn't require a lookup table at all because the error correction is automatically built in, right? In the previous version, as we saw in lecture, we need this whole lookup table. And a big problem with that was that if you have more and more repetition qubits, your lookup table gets huge very quickly and becomes just unreasonable. In this case, we don't even have a decoding table. There's no need for that. Everything gets done within the quantum circuit. And then at the end of the day, you just measure 1 qubit and out you get your answer. However, it's not all amazing. We didn't solve every problem and we can just move on. This is the perfect code. And there are several cons, but probably the most big, or the most important one that might not be particularly clear is that 3 qubit gates are very, very hard to build physically. Generally, you can imagine that the more qubits within a gate or acted on by a gate, it's just going to be harder, right? A 10 qubit gate would be extremely difficult to do. Mathematically, there's nothing stopping that from happening, but physically it's tough, right? So physically it's tough to do this. I mean, acting on 1 qubit versus 2 qubits is actually already pretty hard, but acting on 3 even is harder. It actually, in some sense, literally is exponentially harder. And so in many cases, the Toffoli gate, the CCX gate, would actually be broken down into many more gates, which you can imagine would take way more time to run and may actually introduce more errors themselves. Because one of the pieces where we haven't really touched on here is that in all reality, it's not like the errors can actually be boxed up so nicely as in step 2 here. In all reality, every single thing we do is exposed to errors, right? Now, ideally, we're able to really encode all of these other pieces in the physical hardware so that they're almost perfect and we can really rely on them so you can box it up. But this is really an ideal model. And if we have to break down, say, this last step correction into many more gates, oftentimes C naughts and H's and X's, it's just going to get longer, it's going to take longer, and it's going to be more likely to incur errors. So while the Toffoli does offer some almost magical kind of extra levels of processing and is, again, a very important gate theoretically, physically, it's not common to have that. Now, I will say if there were a physical 3 qubit gate that some company worked on, I would have to personally guess that it would be this one. It is very important and commonly used, but at the end of the day, my feeling is it's probably unlikely to happen, at least in the near term. There are just other approaches that will end up being better. So, okay. Now, I want to stop and see if there's questions. We only have about 4 minutes left. And again, all of these topics are really for you to just explore and ask any questions about. Each week is going to be self-encapsulated. So I'll open up the floor now. The only thing I'll say otherwise is we kind of have 2 other things I can at least touch on briefly with the time, which are we can actually walk through the theory of this code and talk through basically in terms of QETs, why it works. Or we can talk about noise models in Qiskit, or we can just talk about this or error correction generally. My research actually was in error correction in quantum computing, so this is something I'm definitely glad to chat about more as well. But yeah, basically any questions, whether it's on this particular code, or if there's one of these topics you want to dive into, or anything with error correction generally, go ahead and unmute, send it in the chat, or send it to me individually in the chat if you like. Otherwise, I'm glad to kind of wrap up with a quick mention of the noise models and call it a day. Okay, so let's go ahead and again, I won't walk through this. This is kind of some heavy details, but what I will say on this is you can walk through this code using QETs and actually show that at the end of the day, it really will work for a general state, so long as there are only 1 qubit errors, so long as there's only 1 qubit error. Okay. Now, the only other thing I want to mention, and we won't go into the code, it's okay. The code is there, the solutions will be provided. But most importantly, I just want you to understand that there are these ideas of noise modeling. And really the best case I can think of, the most simple case possible to think of why we would even do this is, imagine you build a quantum computer with the error correction built in, say the code that we just used, but then you realize that bit flip errors aren't even really a problem, right? Like imagine we just spent all of this time working on bit flip errors, and I will say they are a problem, so it's worthwhile to have talked about these things. But let's just imagine that they're not that common, or that say the quantum engineers were really good and really aware of this and did some amazing hardware engineering work in order to basically avoid bit flip errors entirely. Well, then it was kind of pointless to spend all this time talking about this theory, and certainly to build a quantum computer with that. I mean, that's a really expensive thing to do. So you want to know ahead of time, before you're building these computers, what the actual noise that the qubits will face is. In other words, we need to model the noise. So modeling noise is a really big part of error correction. Error correction is not just about coming up with the error correcting codes. It's also about understanding what errors we're likely to see. This is really a very nice field that mixes between the hardware, the engineering, the experimental work, and the theory, because the theorists can run off and come up with as many noise models and error correcting codes as they want that are all based on some beautiful math. But at the end of the day, if the physical hardware isn't going to look like that, there's really not much point. So it's really important that both the experimental and theoretical physicists and researchers communicate on this. And that as you're looking into this, that you start to think about, well, what is the noise that we're worried about? Should we be this worried about bit flips versus, say, phase flips? So they come in many different forms, and they address many different types of noise. Qiskit actually allows us to specify and combine them all ourselves. Again, I'm not going to dive deep into this. You can look in the notebook yourselves, but I just wanted to at least give you the idea of the noise model so that you can then look into it. Now, today, we primarily looked at the bit flip code without syndrome measurements. And we talked a little bit about noise models. Again, we didn't dive deep, but I'm always glad to chat offline about that. Next week, we're going to look into networking. Very excited about this new topic, but for now, enjoy quantum error correction. So with that, I will say we're all done. I'm glad to stick around if you have any questions. Otherwise, have a lovely day.
See you later, Adam.
Just answering some questions that have been asked to me individually, but I'll answer generally without mentioning any names or anything, although these are all good questions. First of all, the attendance code, just make sure you write that down. It is